Lesson 9.1 Production API Design Learning Objectives. By the end of this lesson, you'll know how to design and implement a production-grade API for your fine-tuned model, complete with authentication, rate limiting, input validation, error handling, and monitoring. That proof of concept you built in the earlier modules, this is where it becomes something you could actually ship. Plan for about 60 minutes. This is advanced material, so make sure you've completed Module 7 before continuing. Production API requirements. Before writing a single line of code, it's worth being precise about what production ready actually means for an ML API. It means authentication and authorization, so only the right people can call your model. Rate limiting. So one bad actor can't drain your GPU budget overnight. Input validation. So malformed or malicious payloads never reach your model. Graceful error handling, so a bad request returns a useful message instead of a stack trace. Structured logging for a complete audit trail. Prometheus metrics, so you can observe performance over time. Auto-generated API documentation, so your teammates don't have to guess how to integrate. Health check endpoints, so orchestration systems know when your service is ready. API versioning, so you can evolve without breaking existing clients. And caching to avoid recomputing identical requests. Each of these isn't optional polish. They're the difference between a demo and a deployable service. Production-ready fast API template. Here's where the architecture comes together in code. The template starts by defining your application configuration, app name, version, model path, and Redis connection settings for caching. That configuration block is intentionally centralized so you can swap values for different environments without hunting through the code base. Logging is initialized early, before anything else, because you want a record of startup events and failures. Prometheus metrics are registered next. Specifically counters and histograms tracking HTTP request counts and model inference duration. These two metrics alone will tell you most of what you need to know about production behavior. Fast API is initialized with CORS middleware, which controls which origins are permitted to call your API. Critical if a web frontend will be consuming it. The rate limiter is attached as middleware too, enforcing per user request quotas before a request ever touches your model. Model loading happens at startup via Fast API's lifespan event, not lazily on first request. That distinction matters. You want your service to fail fast at boot if the model path is wrong, rather than surfacing that error to the first real user. The health and readiness endpoints. Health and ready are lightweight by design. Health confirms the process is alive. Readiness confirms the model is loaded and the service can actually handle inference. Kubernetes and similar orchestrators treat these differently, and so should you. Testing the API. The test sequence here covers 4 distinct scenarios, and each one tells you something different about your API's health. First, you launch the server with Python production API.py. Watch the startup logs. You're looking for confirmation that the model loaded successfully and that Prometheus metrics registered without errors. Any exception here is a configuration problem, not a runtime one, and it's far better to catch it now. The health check hits /health with a simple GET request. A 200 response with a healthy status means the process is running. If this fails, nothing else will work. Start here when diagnosing issues. The inference post request is the real test. Notice the authorization header. Without a valid API key, this endpoint returns a 401 immediately, before the model ever runs. The JSON payload specifies your prompt, a max token ceiling, and a temperature value. The response should contain generated text. If you see a 422 instead, that's Pydantic rejecting your payload shape. Check your field names and types. The metrics endpoint returns Prometheus formatted output. You're looking for your request counter incrementing and inference duration histograms populating. If those values are 0 after a successful inference call, your instrumentation isn't wired up correctly. Finally, opening the auto-generated Swagger UI at /docs in your browser gives you an interactive interface to every endpoint, useful for manual testing and indispensable for anyone integrating against your API. A single successful request tells you the API works. A load test tells you whether it holds up under real conditions. This script simulates concurrent traffic against your inference endpoint using Python's threading module. The key parameters are the API URL, your authorization key, the total request count, and the thread count. Adjust those last two numbers to match the concurrency profile you expect in production. The makeRequest function sends a post request and records two things: whether it succeeded and how long it took. Wall clock latency, not just model inference time. That includes network overhead, validation, and any caching logic. Threading lets multiple requests fly simultaneously, which is exactly the scenario that exposes bottlenecks a sequential test would miss entirely. After all threads complete, the script computes the metrics that actually matter: total successful requests, mean latency, median latency, and the 95th percentile. That P95 number is the one to watch. It tells you what your slowest users experience, not your average user. If P95 is dramatically higher than your median, you have tail latency issues worth investigating before going live. Production API checklist. Before you move on, run through this checklist against your own implementation. API key validation with user tiers, not just a single shared secret. Per user rate limits enforced at the middleware layer. Eidetic models validating every incoming field. Graceful error responses that never leak internal stack traces. Structured logging writing to both file and console. Prometheus metrics instrumented on every inference call. Redis caching for identical prompts. Both /health and ready endpoints returning me. Swagger UI auto-generated and accessible. Cores configured explicitly, not left wide open. Background tasks handling cache writes asynchronously so they don't block responses. And unique request IDs on every call so you can trace a single request across your entire log stream. If you can check every one of these, your API is genuinely production ready. Next up is lesson 9.2, where you'll containerize this service with Docker. This architecture diagram shows how the pieces you just built connect at a system level. Clients, whether that's a CLI tool, a web application, or an SDK, all enter through a single gateway, typically Fast API sitting behind Nginx. That gateway is where authentication happens first. JWT or OAuth 2 tokens are validated before a request goes any further. Nothing reaches your model without passing that check. Once authenticated, the request router makes a decision. Is this prompt already cached in Redis? If yes, return the cached result immediately, no GPU time consumed. If no, the request goes to the VLLM inference component, which runs your fine-tuned model and returns a fresh response. Running alongside all of this is your logging and observability stack. Every request, every latency measurement, every error, captured and queryable. Notice that observability isn't bolted on at the end. It's a parallel concern that touches every layer. That's the architecture decision that separates systems you can operate from systems you can only hope work. The authentication flow deserves its own walkthrough because getting it wrong has serious consequences. The client starts by sending a post request to the token endpoint, supplying user credentials. The identity provider, operating under OAuth 2, verifies those credentials against its user store. If they check out, it issues a signed JWT with an expiry, typically 1 hour. Short-lived tokens are a deliberate security decision. If a token is stolen, the damage window is bounded. The client stores that token and attaches it as a bearer token in the authorization header on every subsequent API request. When your API server receives a request, it verifies the token's signature and checks the expiry before doing anything else. An expired or tampered token gets a 401, no model inference, no data exposure. Only after successful token validation does the API proceed to return model output. This flow ensures that every interaction is authenticated, every token has a finite lifetime, and your model is never reachable without proof of identity. Rate limiting without tiers is a blunt instrument. What you actually want is a configuration that reflects the real value different users get from your API. The free tier caps at 5 requests per minute and 500 tokens per month, enough to evaluate the API, not enough to build a production integration on. The developer tier raises that to 60 requests per minute and 10,000 tokens monthly, giving engineers room to build and test. The Pro tier steps up to 300 requests per minute and 100,000 tokens. Enterprise accounts get 3,000 requests per minute and 2 million tokens per month, numbers designed around teams running automated pipelines at scale. Notice the pattern. Each tier is roughly an order of magnitude above the previous one. That's intentional. It creates clear upgrade incentives and ensures that a free tier user hammering your API can't meaningfully impact a paying customer. When you implement this in your own system, map these tiers to your actual cost structure. Token quotas directly translate to GPU hours, and GPU hours translate to dollars. API versioning is one of those decisions that feels premature until the moment you wish you'd made it earlier. Version 1, marked deprecated, ran from January 2024 through June 2025. It still exists for backward compatibility, but no new features are being added. Existing integrations won't break, but anyone building something new should not be starting here. Version 2 is the current stable release, active since September 2024. Full feature support, production hardened, and the right choice for anything you're shipping today. Version 3 entered preview in January 2025. It introduces streaming responses and tool call support, genuinely useful capabilities, but it's still in beta, which means breaking changes are possible. Build against it in development environments, not production ones, until it stabilizes. The practical lesson here is to version your API from day one, even if you only have one version. Adding versioning retroactively means coordinating breaking changes with every existing client simultaneously, a coordination problem that gets harder the more successful your API becomes.